Okay, good afternoon, everybody. Good evening. So the talk for today will be by Igor Korepanov from Moscow, and he will be talking about the Tetrahedron equation and related structures. So, Igor, if you could please start.
Yes. It's just a moment. Okay. Hello, everybody, and I am very glad to have this opportunity to do this talk here. My talk is about functional tetrahedron equation, and it is okay. It is mostly educational. It is not about any newest achievements, but rather about some oldest work, oldest discoveries. Okay, but thank you for your interest anyhow. The usual, okay, and I have sent a direct link to these slides on the chat of this Zoom session. Okay, here is the usual picture of tetrahedron equation, and it has several varieties. Several varieties of equation which are depicted using the very same picture. Maybe the most popular is the quantum tetrahedron equation, but there are also other things, and I will be speaking about set theoretical tetrahedron equation, which looks like here. You have 6 input variables. Well, they belong to some set, and actually they sometimes they belong to 6 different sets, and then some functions here, S capital, all the 4 S capital are just functions. Each of them acts on 3 of these 6 variables. And well, I believe that everybody of my audience know this very well. I just remind you this standard picture about how they act and what is the equation itself. Well, in principle, as I said, these 6 variables that are somehow transformed by these S capital, by these 4 S capital, they may belong to different sets, and so these 4 S's, they, in principle, they may also be different or they may be essentially the same. That might be either way. Okay, then only one thing. This letter S capital with different subscripts, so may denote different functions. And one more comment is that these functions may be also not strictly speaking functions in the set theoretic meaning, in the set theoretic sense, because they also may be, for instance, birational, so that sometimes they give, loosely speaking, they give either infinity or something that is not well defined, but that may happen only in some isolated points. I said something about birational, but they actually may include something such as square roots, and also there might be some singular points. Okay, then go to the next picture. Here we see also some standard picture where the numbers are the same as in this previous picture. So each number here corresponds to a line, but here the previous picture is intersected by one more plane, and so each line, when it intersects this plane, gives clearly a point, and there are these 6 points, and when we move this auxiliary plane, move it somehow, something may happen with our triangles here. For instance, one way that corresponds to this left, okay, to this left-hand side of this picture. Here it the triangle 3, 5, 6 is the first one to be turned inside out. Yes, yes, somehow. So if we turn inside out this left-hand side triangle, how does it happen? It happens something like, for instance, you draw this line here, and so it is not like this, but now like this, and this green triangle is now here, and then you do those transformations. Well, I don't want to stop very much on this. Sorry? I don't want to speak very much about these transformations because they are standard, and actually all people most likely know them very well. Okay, now I begin explaining something specific for my work. Let me draw just one line in a plane, and this will symbolize the following. To the whole plane corresponds some vector space, finite dimensional vector space, with dimension n, and the line called A, it divides the plane into two halves, and by definition, there are some linear restrictions, k linear restrictions, corresponding to the right half of the plane and to the left half of the plane. Well, okay, I think you can see this all. And so if all restrictions, linear restrictions, if they all are in the general position, then we can say that to each half of this plane corresponds a space of dimension n minus k. And on the plane, on the line, is by definition V itself. So that's all about this strange picture. But let us see what happens when we have two lines. When we have two lines, we will now have a matrix.
Igor, I'm sorry. Could you return to the previous page?
Could I what? Sorry.
To the previous page. Previous page.
To the previous. Yes.
What is the dimension of the space V? Okay. N. K.
The dimension of the whole of the space corresponding to the whole plane is here n, and line called A imposes k linear restrictions on its right side and k other linear restrictions on its left side. So,
but what does it mean? What do you mean by linear restrictions on each half? I don't know.
Okay, linear restrictions just means that
the point of the Grassmann.
Okay, that you select somehow a subspace of dimension n capital minus k, or you can say that there are k linear functionals that must be equal to 0. You see, let me just say that we will be soon considering a more concrete example where this space, vector space V, will be the space of meromorphic functions on an algebraic curve with some restrictions on their divisors, pole divisors. And imagine that you impose such restrictions. You select k points in this curve and say that on the right hand side, all meromorphic functions from this V must be equal to 0 in some chosen k points, you see. So in my concrete examples, these restrictions will just mean that meromorphic functions must have k additional zeros to additional to whatever conditions had been already imposed on these functions. Okay. So now but I am now speaking about the most general setting. And as for algebraic curves, they will appear soon. Now, imagine that we have a picture with two lines in a plane, two lines, and moreover, there are some integers called m and n. Okay, like this, called m and n, and the dimension of the whole space corresponding to the plane is their sum. N capital is m plus n. So what will correspond, for instance, to this half of this line? It lies to the left of line A. Left, you see here letter L. It lies to the left of the letter L. So in my pictures, to this line will correspond a subspace of this V of dimension, you see, n minus m equal to n. So to all these fragments, let me color them in some arbitrary colors. Okay, like this, and for instance, this is like this. So to all these four fragments correspond some linear spaces, and to this and this linear spaces of dimension m, and to this and this of dimension n. And now I want to define a matrix called A beautiful. Matrix A beautiful will be actually block matrix of dimensions n by n, and it is okay. It is defined as follows. Just take some bases in all those subspaces, in subspaces VBL, VAR, VAL, and VBR. Takes any basis, and okay, denote them like it is written here, and make columns of these basis vectors, and define matrix A beautiful in this way. So you see, is it clear? So this matrix is determined up to what I call a gauge transformation. Gauge transformation in my report will always mean other choice of a basis somehow, somewhere. For instance, what is this M1? M1 corresponds if I choose basis here in another way, then M1 is a matrix that transforms one basis into another basis. Okay. So what I was already telling you was one line in a plane, two lines, and let here, for example, be many lines. For instance, four lines in a plane. And line A gives m restrictions on the right of it, and also m restrictions, but other restrictions on the left of it. And all of these linear restrictions are, I remind you, in a general position. They're generic, no casual coincidences or whatever. So if we have these lines like this, then what this example must tell you is what space will correspond to this fragment of line D. Okay, to this fragment will correspond the space already written here and of dimension equal to Q. So because it lies, this fragment lies on the left hand side of my directed line A, and so on. Okay, so these were maybe strange pictures, but interestingly, they give you at once this functional tetrahedron equation that is, of course, when we speak about it, it will hold up to gauge transformations, that is up to choosing bases in all these subspaces. But anyhow, it will be here very soon, that functional tetrahedron. Now consider such refactorization problem. Let you have block matrices like here, and okay, what are those? But never mind. So let the sizes, dimensions of these blocks be like this, M and R, for instance, and everywhere the same. So these diagonal blocks are square, and non-diagonal blocks are either square or not. That doesn't matter. And consider this refactorization problem. You have these three block matrices, and you want to build these three block matrices from them. So this is what I want to consider now, and what is below is just a picture that corresponds to this refactorization problem. If you have somehow solved this refactorization problem, you will have gauge freedom. This gauge freedom corresponds, of course, to what I was saying here about different choice of bases. So this is all very simple. And just if you look here at this screen, then of course the product of new A1, A2, and A3, just look here, is clearly the same as the product of the old A1, A2, and A3. So this is just a trivial thing about this gauge freedom. And here already is a theorem. This refactorization satisfy functional tetrahedron equation. But okay, I must probably say that this refactorization problem is solvable first. Why is it solvable? Because you can look at this picture in this screen, in the lower part of this screen, and okay, let us return a little bit. Let us return here to these lines with these linear restrictions corresponds matrix A, but you also can take, okay, you can reverse this all. Take first A, let A be given, and then can you define these linear restrictions given this A? Certainly, yes. You must okay. What you have first is just this A. Then you say that let there be a space V whose basis is composed of some basis of some m plus n vectors, and call them like this. Then you have, as I said, this matrix now given to you, and you construct this, you construct this new basis x prime like this, and y prime like this, just from this relation now acting as a definition. So what I wanted to say is just if you have a matrix A given, you can draw this picture starting from this matrix. And if you have now this refactorization problem where initially you have given to you these three matrices, okay, you can just think a little bit, not very hard, and understand that you can put in correspondence to these lines such linear restrictions that will correspond to the left-hand side pretty well, and then using the same linear restrictions for each line, you get a solution of this refactorization problem. Okay, so if you have now not just 3 but 6 matrices, you see everywhere here are some matrices A with some probably subscripts. So 6 matrices are given to you, and then you can first you can obtain from them 6 new matrices. Let them be dark blue, like here. And second, you can obtain them in doing this refactorization, a sequence of 4 refactorizations in 2 different ways. And why will you obtain the same dark blue matrices in these 2 ways? Just because of what I was saying about those pictures where you have lines in a plane, and to each line correspond some linear restrictions. They are they do, in the right hand side, they do not depend on the way in which you obtained this right hand side from this left hand side. They don't depend on a specific way, but they are just they just correspond to this picture and all. So this functional tetrahedron equation follows from almost nothing. You see, but we must keep in mind all these of course gauge transformation. For instance, you have this okay, you have this fragment of the line, so you can apply some m, for instance, here, and then you must apply m to -1 here. These are gauge transformations. So this functional tetrahedron equation is up to gauge transformation. And okay, and what are actually the parameters on which these S's act? They are if you parameterize your matrices A by some parameters, or maybe just these A's as such, you have just these A's and they are transformed somehow. So this is a functional tetrahedron equation where the sets on which those S's act, the sets, there are 6 sets, and they consist of these block matrices A. Okay. Again, I would like to remind you that this, of course, works for a general position, and of course, there are many many possibilities of making something singular, but I don't delve into that. I just let everything be in a general position. This general setting of a functional tetrahedron equation is very simple. What is not very simple is somehow in imposing some actual gauge on this all. And what Sergeyev did and what was very good is that he provided some explicit solutions with, in my terminology, with explicit gauges everywhere. That is, with no freedom like this. Everything was fixed. Okay, now.
I can ask something, Igor. Can you give any reference of the?
Yeah, I am very sorry, but I cannot hear you distinctly. Can you maybe write in the chat or just go to your microphone?
Can you please give any reference of the proof that you presented?
I think that you see, I think that it is in the paper called like this. In this paper, and if you have a PDF file that whose link I have provided in the chat, if you have that PDF file, then you can just click on this, click on where I that paper. Well, of course it was written very long ago, but I think as far as I remember, the proof must be there. Okay.
Okay, thank you. I'll check it out.
Sorry. Now something about algebraic geometry. You see, I am speaking about something exactly solvable, and all solitonic people know that an algebraic curve must correspond to all such things. So consider once again this. Consider this refactorization problem. Okay, refactorization is when you have something like this and then you make something like this. This is refactorization, and simply factorization is if you have something like this, just a matrix, just a block matrix like this, with three inputs, so to say, and you factorize it somehow. So this is factorization. Let us consider this factorization, and you have this matrix A beautiful, and you define an algebraic curve, some algebraic curve corresponding to it, and given given by this system of two equations. And also, it is important that it lies, for instance, not for instance, CP3 or whatever, it lies exactly in the direct Cartesian product of three projective lines over complex numbers. Why it is important? Because we will have to consider different possibilities here. For instance, you see, by definition, V is the product of U by W. And one possibility when it happens might be like this. V is finite, for instance. U may be 0, and W may be infinity. Or, for instance, V may be again finite, but both V finite and no, sorry. U, for instance, U may be finite, and then W equal to infinity, and V also equal to infinity. And in my paper, which is also the reference to which is in the beginning of this file, such possibilities are considered, and they are important. So, it is important that my curve gamma lies in this direct product and not anywhere else. Okay. What does this first equation mean? Okay, we will look here a little bit later, but the first equation mean, just look at it once more. If the determinant of some matrix is equal to 0, then there is a vector that is annihilated by this matrix. So this first equation means that there is some vector x beautiful, some block vector, if I may put it like this, that satisfies this relation. Okay, and what is written here? Okay. Well, and return now to this screen. If you carefully consider all these points where for instance, what I lost this. Let me restore here something that I have written. For instance, consider such possibility where V is finite and U equals 0 and W equals infinity. So this can be very well, and there are some points on curve gamma where this exactly happens. And the such points, by definition, so U is 0, W is infinity, U is 0, W is infinity. They correspond to some divisor that is called here D4. So D4 is some D4 consists of n points. Why n? Okay, you can just if you do some linear algebra, some exercise in linear algebra, you can understand why exactly n. So D4 is a divisor of those points where U is equal to 0, W to infinity, and V is finite. And also, besides D4, there are also other divisors consisting of some points where something other happens. For instance, D1 is where U is infinity and V is infinity, and so on. So again, if you do some simple linear algebra, you will see that on this curve you will have some divisors of such degrees as written here, such that, for instance, U infinity consists of D1 and D2, and where is D2? D2 is where also W is 0. So if W is 0 and U is infinity, then V is just finite. So some careful consideration give you this picture as described on this page. And these divisors will be important soon, at least two of them. Okay, now okay, I am grateful to Igor Krichever, who taught me, from whom I learned what to do with these vectors like this X beautiful. Namely, it is determined up to a scalar factor, and then you normalize it somehow. For instance, take some coordinate and order it to be equal to unity, just everywhere. Then you have a meromorphic vector on my curve gamma with a pole divisor that we call D. Okay, but if you consider these components separately, they satisfy stronger restrictions. Well, I wrote here as we are going to see, but how to see this? You see, you multiply matrix A by this X and obtain here X multiplied by U. So if you just think about it a bit more, you will discover that X consists of vectors that have additional restrictions as here, not the meromorphic, my meromorphic vector X beautiful, for it only this D is relevant. But if we take separately its first vector component X, then there are more restrictions for X capital, for Y capital, and for Z capital. Okay, so they are like this, and okay, what is written here is okay. If there might be some pedantic people in my audience who will ask me whether I checked whether I have checked that the properties of this curve gamma and of this divisor, and whether everything with everything connected to Riemann-Roch theorem is here takes really place. So yes, of course, and you can see that in my paper referenced in the beginning of this file, and here I just wrote that the genus of curve gamma is as follows, and the degree of the whole divisor of the meromorphic vector is as follows. Okay, now what is especially beautiful with these divisors is, okay, is in this picture, but let us return here first. This algebraic curve gamma is conserved under some kind of discrete time evolution. And this discrete time evolution will go as follows. I first take that matrix A that we have seen already, and then factorize it like here. And after this, we reverse the order of its factors and make new matrix called B beautiful. So we took this A beautiful, and then we made this B beautiful. And this is by definition one step of evolution of this dynamical system. Okay, of course there are, it goes again up to some gauge transformations. That's no doubt like that. Now, what is good about that algebraic curve in connection with this evolution? You see, look at this picture. At each edge, there are two numbers. There are two numbers that correspond to nothing else but linear restrictions. But linear restrictions for meromorphic functions on different segments of these edges. For instance, here, here, or somewhere else here. Here you see 2 and 6.
Yes.
That is.
I'm sorry. Could you go back to the previous page?
This?
Yes, this refactorization and the, if you want, the degree-free envelope of the Darboux transformation. For example, in the orthogonal group where this refactorization is the choice of Euler angles, this reverse of the product order, it is an exchange of two of the Euler angles, isn't it?
Okay, if I heard you well, you were speaking about a particular case where all matrices are scalar. All these things like these A, B are scalars, and moreover they are orthogonal, and you have Euler decomposition and.
Just to clarify the situation, in this singular case, is it the reversement of two, a transposition of two of three Euler angles?
Sorry, why transposition of two?
Of the first and the third.
Yes.
Okay.
Yes.
You say that this is a solution of the tetrahedron equation.
Yes. You see.
Okay.
This is of course a solution of functional tetrahedron equation, and moreover, it is also somehow isomorphic to something with Ising model to something. There are many beautiful things about the case that you were asking me, and it somehow corresponds to Ising weights also. But here in my report, I am speaking of a general case. Just everything you see. There are, of course, very many beautiful and very non-trivial things in different particular cases, and also they are very difficult, of course. And I am speaking here about a general position of everything, where interestingly everything is very simple. Okay, so now please look at this picture about these divisors, and compare this picture to something else. Okay, this picture, and now I return. I return where? Okay, for instance, I return here. Or no, just please wait a little bit. No, I will explain you simply on that picture. Oh, so sorry. I am very sorry. I will. Okay. Just look at this picture as such. And for instance, look at one line here. Let it be, for instance, this line. What we see to the left of it, we see to the left, we see okay, just one moment. To the right of it, we see this divisor number 4. And to the left of it, we everywhere see this divisor number 2. Okay, let it also be red. If we take this line and look carefully at this picture, we see that there is again this space, linear space V, consisting of meromorphic functions. And this line, for instance, it brings about such restrictions as restriction number 4 to the right of it and restriction number 2 to the left of it. Now take one, for example, take one more line. Let it be this. So to the left of it, you have always this divisor number 1, giving restrictions, and to the right of this line, you have everywhere you have these restrictions number 6. So
sorry, restriction on what? On function?
Yes. You have V is a linear space of meromorphic functions. Meromorphic functions, which are everywhere the divisor of function plus some fixed divisor D must be positive. But there are also additional restrictions. Additional restrictions in this setting are just requirements that functions must be 0 in some set of points, you see. And what I wanted to say here is that this picture about divisors fits very well in my more general picture that was in the beginning of my talk, like this. A line gives you some restrictions to the right of it and some restrictions to the left of it. And 2 lines, each of them gives restrictions to the left and to the right. So this picture about divisors, is about the same thing. Okay, now there is something more. There is also something more. And something more happens when you actually do this. Actually, when you reverse this order, like this, because looking at this picture, we can say something about separate matrices A3, A1, and A2. Namely, they act. Where is? Namely, this B here is determined by the following relation, where those primed X capital, Y capital, and Z capital are meromorphic vectors appearing on these inner fragments of my lines. Okay, so maybe I can just say that if you look carefully at this all, you you will see that this is really like this. And as B is determined by such relation, the same algebraic curve corresponds to B beautiful, and divisor D changes with each step of evolution. It changes linearly in that discrete time. So when discrete time undergoes one step, this thing is added to the divisor. So what you obtain is a very classical and well-known thing for those people who work in any solitonic matter.
Igor, I'm sorry. Is it an analog of the vacuum curve?
You see, for me, it is, and it is a very, very big analog, because I am describing my paper that I did after another paper, and in that other paper there was a similar algebraic curve, conserved algebraic curve, and that algebraic curve was exactly the same curve, the same vacuum curve that I learned from Krichever. So for me, this is, of course, for me personally, this is a very, very big analog of vacuum curve. Krichever had his own setting, and I have other setting, but in my work previous to this work, the curve, the problem was different, but the curve was exactly Krichever's vacuum curve.
But is it an analog for the tetrahedron equation? Originally, the Krichever vacuum curve was defined for the solutions of the Yang-Baxter equation. It is also for the Yang-Baxter, or maybe for local Yang-Baxter.
You see, here, this refactorization is, of course, you can call it, really, you can call it local Yang-Baxter, of course.
Okay.
So tetrahedron comes from local Yang-Baxter. So what I am telling you now is like this. Yes, tetrahedron comes from local Yang-Baxter, and local Yang-Baxter is nothing else but this refactorization.
So it's some parametric analog of the vacuum curve. Isn't
Parametric.
Yes.
What do you mean by parametric? You see. Everything is very much interconnected here. Everything is interconnected, and I am telling you about functional tetrahedron, but also there is something that relates quantum tetrahedron, to vacuum curves, and I don't remember, somewhere in the beginning of 1990s, these years, I discovered a solution to quantum tetrahedron, yes, starting from vacuum curves. But here, in my current report, the situation is different, however. So, it is not about quantum.
Excuse me once again for interrupting you. Thank you.
Okay. Okay. So now about this this dynamical system in discrete time. This dynamical system that gives you from A capital A beautiful, this B beautiful. Something about it. So you have sorry. You have this here is here is the system of equations that gives you this vacuum curve, or not vacuum, this anyhow this curve gamma. And this curve is exactly what is conserved, and it can be written also very making a very simple transformation. It can be written like this. So integral of integrals two parametric family of integrals of motion is like this. Okay, so you see, yeah, I have a dynamical system and integrals of motion that go like this. Now, okay, just a few comments on this. If you have an algebraic curve, then and it is conserved, it is given by some essentially polynomial equation. That polynomial equation is defined up to any constant factor, and also you must be sure that the curve is irreducible. It does not consist of many components, but all that works for my curve, and also a constant factor can be fixed as is written here in this slide. So we have integrals of motion, two parametric family of motion integrals. Now consider some reduction of this dynamical system. Reduction means that your matrices have some specific form. Your matrices have some specific form. Namely, first take a triangular lattice like this, and let it be situated on a torus. On a torus, for instance, okay, torus may be as you like. For instance, something this may be closed here. You see, just if you want, and okay, and for instance, this may be closed here, or whatever you want. It just is somehow situated on a torus. And let my space V be such that there is exactly one basis vector for any edge here, for this edge, for instance, for this edge, for this edge, and how many colors do I have? So to any edge corresponds one-dimensional subspace, or just a basis vector, by definition. Okay, then let us impose some special structure on this matrix A beautiful. Let me remind you that this A beautiful, okay, let me do it like this. This A beautiful is a block matrix like this, is a block matrix, and for instance, take this A plane capital and require that it has that most of its matrix entries are 0, except for some special matrix. For instance, for this A corresponds to horizontal edges. That is, what does this mean? Just it acts in the subspace corresponding to all horizontal edges on this picture. And matrix entries are non-zero, only are allowed to be non-zero only if input is here, then output is here, you see. And for instance, matrix entry between this and this, such matrix entry is 0 by definition. So this is a special structure, and okay, I don't know how understandable it is, but let us consider also this, for instance, this D, well, edges horizontal, then vertical, and then oblique. And here also horizontal, vertical, and oblique. And this D acts from what? It acts from horizontal to vertical, yes. And for this D, if horizontal is here, then vertical may be only here. Otherwise, its matrix entry is 0. So consider such reduction of my dynamical system. Okay, and consider evolution of this dynamical system. You factorize each, so to say, local matrix, you factorize, and what you obtain is something like this. And the whole picture is what is called Kagome lattice. The whole picture that you obtain is Kagome lattice, and when you apply this dynamical system to this kind of model, okay, you can describe what happens. For instance, you can describe it as follows. these oblique lines travel through these intersection points, and so this is how this evolution goes ahead. Now what does this, what do these motion integrals give for this model? Okay, there are some technical things, but maybe I just go here first. What they do is as follows. This two parameter family of motion integrals is essentially the same as statistical sums or partition function or state sum, it is called, for a two-parametric family of six-vertex free-fermion model. Let me remind you that six-vertex model is a quantum, in a sense, model that were defined on some lattice, and each edge, okay, let it be like this, for instance, or let it be already Kagome. Each edge is allowed to be either thin or thick. So, for instance, this can be thick, and if this is thick, it goes here. Some of these also must be thick, and otherwise Boltzmann weights are 0. So the only situation at each vertex where Boltzmann weight is not 0, there are only 6 such situations depicted here by definition. And this is why this is called six-vertex model. Six-vertex model, and this specific form of one of the weights is called free-fermion condition. So you must do something for these multipliers U and W. Just add them, or better to say, multiply all these things by something like here, and you will obtain that statistical sum or partition function that is almost the same as my already written family of integrals of motion. Oh, sorry, here is a typo. To be exact, they are interconnected. Okay, there are some technical things related to the topology of cycles on my torus. So they are interconnected as is written here. But essentially, this family of motion integrals is practically the same as this family of statistical sums. So again, where U and W in statistical sum, you just multiply these weights as is written here and take notice that such multiplying does not violate this free-fermion condition. Okay, I have almost finished, but what I want to say, just this work, just there is one more paper, and it is exactly, it was done even earlier than my paper that I was speaking about, and it was about vacuum curves, or better to say, the same curves that were called vacuum curves in Krichever's paper. So there is one more similar model where I did not find how to I didn't find a functional tetrahedron behind it, but probably it does exist, and I even suspect that there are some young people who already know the answer to this exercise. So I myself did not do this exercise, but there is a similar model where I think tetrahedron inevitably can be applied also. And this model, this other model, begins as follows. You take a simpler block matrix where all dimensions are n. All matrices are square, all submatrices of this block matrix are square and of the same sizes. And once a step of evolution is the composition of two things. First is you just take the inverse, and second is you block transpose these two blocks. So this is an exercise that I would like to mention, and I did not do it in the sense that okay, there is also a conserved curve, vacuum curve in this model, and divisors that travel linearly during that discrete time. But I don't know how to apply functional tetrahedron to it, but I think, and it is related to dimer model, and I think there are some young people who already know the answer, how to apply functional tetrahedron. Okay, and now to finish my report, I would like to, okay, my report was mostly based on a paper written in the winter 2014 27 years ago. So what will be popular when 27 years from this year pass? Okay, I think that popular subjects were higher polygon equations. You see, there are simplex equations. For instance, simplex, this is Young-Baxter, tetrahedron, and so on. But there are also polygon equations closely related to them. So Young-Baxter and tetrahedron are more or less studied, and there are also many interesting works about pentagon, but don't forget that there are also higher equations. And maybe in the coming 27 years, some new algebraic structures will be discovered on this way. Okay, so thank you very much for listening.
Thank you very much. So are there any questions?
May I ask a question?
Yes, of course.
I wanted to ask about this local Young-Baxter equation. How should one understand this? So usually Young-Baxter equation is an equation where our matrix X acts on the tensor product of two vector spaces, and in your case, this A matrix acts on the direct sum. So
Thank you for this question. Okay, direct sum, direct sum plus free-fermion condition gives you, no. Sorry, I will correct this. Quantum, which is the same as tensor Young-Baxter, if you impose free-fermion condition, it is practically the same as direct sum.
So are you saying something like that Clifford algebra of the direct sum of two vector spaces is almost a tensor product of two Clifford algebras?
You see, if you take this, take direct sum Young-Baxter first, then interpret it as acting on fermionic creation and annihilation operators. You see, if you have some matrices in that direct sum, creation annihilation operators, then those matrices act on they act on some, okay, you have some matrix, it must act on some column of something. So you just write here some creation, annihilation operators, fermionic. And then third, you do some simple trick using, you see, there is some such thing as Jordan-Wigner transformation between fermionic, that is anti-commuting, fermionic anti-commuting and spin variables. So there are these three steps. And when you have done these three steps, you obtain from direct sum Young-Baxter, you obtain quantum dynamical Young-Baxter. Dynamical just means that dynamic Young-Baxter just means that okay, first I write not dynamic but simple Young-Baxter is like this, and dynamical means that there are some different guys here. So again, if you have a direct sum dynamical or not dynamical Young-Baxter, that doesn't matter. If you have Young-Baxter in a direct sum, then you using in some simple but clever way fermionic using fermionic creation annihilation operators, you can obtain quantum Young-Baxter. This does not work for tetrahedron because that trick with this Jordan-Wigner transformation, it depends somehow on the topology of a two-dimensional plane, and for tetrahedron everything happens in the three-dimensional space, so it regrettably it does not work there.
Yeah, thank you very much.
Mm-hmm.
May I ask one more question?
Okay.
So, is there any relation between this free-fermionic six-vertex model and some dimer model on some lattice? I'm asking because partition function of any free-fermionic model should equal to some determinant of some matrix with a lot of zeros and so on. So there should be probably some relation.
Yes, I can at this moment I can only answer you that that of course they are very similar things, and of course there must be some relations, but I am not ready to give you right away many details. But they are of course very similar, and informally they are almost the same thing, I think.
Thank you.
Okay, Igor, can I also ask a question?
Yeah, yes.
So, you said that this matrix three-factorization problem is equivalent to the tetrahedron equation. So the story in the case of the Young-Baxter equation is that if two matrices are uniquely refactorized, in other words, if a matrix refactorization problem uniquely defines a map, this map satisfies the Young-Baxter equation, not always, but if an additional condition is satisfied, if the trifactorization property implies the trivial solution. So it is written by Papageorgiou and Kouloukas. So I was wondering what is the analog in the case between matrix trifactorization property and the tetrahedron equation?
You see, again, I cannot tell you much about Young-Baxter right away. Probably you know that better than I. But what I think is that tetrahedron equation, is it equivalent? I did not say about equivalence. I said that this matrix refactorization problem provides you solutions to functional tetrahedron equation.
Okay.
It provides, and no additional conditions are required. So I think that in this sense, actually, tetrahedron is simpler and maybe even somehow more fundamental than Young-Baxter. You see, because it does not require any additional conditions. And as for Young-Baxter, and what I know is, of course, that there are many other refactorization problems, but I am not prepared to discuss them right away.
Okay, so I would guess that you would have something like to put 6 times a matrix in a row and refactorize this thing. That would be kind of the additional condition. But well, I tried it and it doesn't work. But you know, if the matrix refactorization problem defines a map, is not necessarily a tetrahedron map. Well, if it defines uniquely, probably you are right. But I don't know is there any proof about it. So if a map uniquely, if a matrix refactorization problem defines uniquely a map, is this map the tetrahedron equation?
You see, in my case, I did not speak about unique matrices. Everything happens, in my case, everything happens to within these gauge transformations. Like here on every edge in a picture like this, there may be made some gauge transformation. So this M, for instance, belongs here. This M inverse and this M here. So in my case, there is an equation that is right to within this gauge transformation. And if you want to fix all gauges, then this is okay. This is a separate problem and very interesting. Was it what you were asking about or not?
Well, I think I will try to formulate my question. I will write to you a little bit later, I will write to you and I'll try to formulate the question.
Okay. Okay, thank you.
Very much for your answer. So, are there any questions?
Yes, could you please repeat again the very basic thing about the relations on vector spaces? In the beginning, I didn't catch the concept. So you say that the vector space is corresponding to the whole plane, and then you say that the line on the plane imposes some relation. Relation on what?
Okay. These are just pictures. You see, I like pictures. And by definition, if I draw a picture like this here on the screen that you probably see, you can see, then this picture with one line, it means that first there is a again, first there is a vector space. Just by definition, if I have a plane in my picture, then there is a vector space called V. And if I have a line, then I have two subspaces. I just have two subspaces by definition of dimension like this, and all. That's all. I used this word restriction. Okay, I simply like this word for some reason. But if you have a subspace of codimension K, that is dimension is n minus K, then you can always say that there are this subspace is somehow cut out of a big space by K linear restrictions. Why not? Especially so because in my concrete examples with that algebraic curve and divisors, these linear restrictions are very, very transparent. There are really K points on that algebraic curve where I impose a requirement that in that point, in any of those K points, the function must be 0, you see?
The K was 2, yes, in this case, because you had two points, like two divisors.
No. K is any integer.
No, in the example where you had these algebraic curves, you had two divisors attached to each line. Yes.
Yes, I have two divisors. Yes, and in here I did not speak about divisors, but also I have two different spaces. This and this, and all of both of them are of such dimension, like this. Well, and if you have several lines, for instance, 2 lines, then each of them provides restrictions, one set of restrictions to the right of it and one set of restrictions to the left of it. So, and
can I think that we associate with each corner some like intersection of two spaces defined by restrictions from these lines?
What do you mean by corner?
We have on this picture we have 4 corners, like.
Yes, yes. In this picture, we have 4 corners, and but we are not very much interested in these corners. You see, yes, there are 4 corners for subsets of the plane like this. Of course, they are here, but in such picture like this, we are not interested in them. Actually, we are interested in such. Here we are interested in such half lines as, for instance, this thing, and the restrictions on this half line is the restrictions are given by the condition. You see, the half line belongs to is a half of line B, but the restriction is imposed by line A. Okay, so we are not really in this picture. We are not really interested in these corners. And if we have a more complicated picture like this, if we have a more complicated picture like this, again, we are here. The plane is divided in many subsets, like, for instance, this one. But we are not interested in it. We are interested in what happens on these line segments, like, for instance, this one. You see, in these restrictions, and what exactly happens is already written here. Just you can look at it once more and see that this is a fragment of line D, but restrictions are imposed by 3 other lines, A, B, and C.
Yeah, okay, it's clear. And so there is no any object on this picture which can be associated with parts of plane, like with polygons.
You see, in this picture, you are right. There are no objects, but maybe if we think a bit more, there might be such objects, but I was not speaking of them. Yeah. Maybe there may exist interesting objects associated with polygons with parts of the plane.
Thank you.
So, okay, are there any other questions? Okay, then maybe we should finish. Igor, thanks so much for your talk.
Thank you very much all for listening. I've seen here many of my friends. Thank you all very much for joining my report.
Thanks again.
Thank you.
Thank you.
See you.
Thank you.
Bye-bye.
Thank you.
Thank you.
Thank you.
Bye.
Bye.